7.3% composition. We are looking more at applications now. We're at the point in our semester where we're kind of done with new concepts and we're just learning to apply the things that we already know. So 7.3 is like the very last new thing, and we're going to take the mole and we're going to use this information that we learned today and the mole, and we're going to next week be able to take percents of a given compound and calculate the formula for that compound. So what we're doing today is we are taking an actually known compound and breaking it up into percents. So for example, we have air here. The air in our atmosphere is 78% nitrogen, 20% oxygen, 1% water, a bunch of other small percents of different gases. We're kind of doing that today. And next week we'll be doing the reverse, where I will give you a percent and you will be able to figure out the compound. So think in a situation if you were in a lab and you had an unknown compound and all that you had was data on particular elements that the compound contained, which happens a lot. If you have, it wouldn't be by mass percent, but you could have combustion analysis data where you get percents of different elements and how prevalent they are, or you could have a mass spectroscopy data set where you actually do get the masses of different portions of the compound. So that kind of reverse engineering of a compound structure happens all the time. First, so I want to focus on the macroscopic scale. What I've done this week is you might have seen an optional egg lab, and if you haven't done it yet and you have the means to, I would suggest that you complete the egg lab before you move on with this video. But what you are going to do is you're going to do the percent composition calculations essentially on a macroscopic scale before we break it down to the microscopic scale and deal with elements and atoms, molecules. The purpose behind this, because it's not really a scientific lab, is it's all about the method. So the method that you use to determine what part and what percentage of the egg is part shell, part egg white, part egg yolk. And I will explain what I mean by that in just a slide here. But the method behind how you figure this out is very much reflective of how you will do it on the microscopic scale. So I figure if you can understand how to do it with something you can hold, then you can understand how to do it with something that is much too tiny for us to really even think about. Alright, if you have done that lab, then you find that the percent composition is most easily accomplished with finding the percent by mass. You could also do it with volume, but it gets too difficult to do that with particles because we don't have really a volume for atoms or molecules. So we do it with mass instead. So we're going to do it with mass with eggs, and then we're going to break it down and do it with mass on the particle level. Either way, the equation that we use stays the same. So the mass percent, which is what we're solving for in percent composition, is equal to a mass of a piece of whatever you're looking at. So in this case, part of the egg divided by the mass of the entire egg times 100%. Let's say, for example, I had an imaginary egg, and I was concerned with finding the percent of egg white in the egg. Okay, that percent of egg white, right? The mass percent is equal to mass of part of the egg. So in this case, the mass of the egg white. So let's say the egg white itself was 100 grams, and that is divided by the mass of the entire egg. So let's say the egg is 200 grams, which is probably a large egg, but it'll do for this purpose. So part of the egg, right, the egg white is 100, divided by the entirety of the egg, which is 200, and then you multiply it by 100% to get it into a percent. If you crunch the numbers, it turns out that 50% of the egg is made up of egg white, right? Because 100 grams divided by 200 grams, that's 1/2. So half of our egg is egg white. We're going to take this same equation and we are going to switch over to talking about how we would do it if it was a compound instead of an egg. It's still mass percent is equal to part of the thing divided by the whole of the thing, okay? Or the mass of one element in a compound divided by the mass of the entire compound, and then times 100 to get it into a percent. If we did this with CH4, let's see what that would look like. Now, when I was doing the egg problem here, you notice I worried just about the egg whites. We would have also had to do calculations for the egg shell and the egg yolk. So when I do the CH4 here, we need to do calculations for carbon and for hydrogen. Now the mass of CH4 is, let me look this up really quickly. I know it's 16, I think it's 0.04, but let me calculate it really quickly. So 1.008 times 4 plus 12.011, yep, 0.04. Okay, so that is grams per mole, right? So that is the mass of our compound. Now, let's say we're solving for carbon's mass percent first, right? So the percentage of carbon is equal to, and let's go back and look at our equation, the mass of 1 mole of a single element. So right now we're talking about carbon, so it's the mass of 1 mole of carbon. Okay? So 12.011, remember, get that off the periodic table, and that's grams per mole. And let's see, it is divided by, and we look back at our equation, the molar mass of the compound. So the mass of the entire thing, which we have already found, right, 16.04 grams per mole, and then it's multiplied by 100 to get it into a percent. That works out to be 75%, just about. Okay, I'm rounding a little bit, but it's just about 75%. If we do the same thing with hydrogen, and we take the mass of hydrogen, 1.008, and if it's alright with everyone, just to kind of save space and time, I'm not going to write the units, grams per mole and everything, because I hope that it's apparent by now where we're getting that. So I'm just going to write the numbers. So 1.008 grams per mole. Now this, okay, needs to be multiplied by 4. And think about it for a sec. Why? Because in our molecule, there are 4 hydrogen atoms. So if we are talking grams per mole, then we need to account for 4 hydrogen atoms in our molecules, which will end up being 4 hydrogen, in every mole. Okay, 4 counts of hydrogen in every mole. So whatever the formula is written as, you need to multiply your masses by that much. Hydrogen in this case is 4. Carbon would be, I guess, multiplied by 1 if you wanted to be real mathematical about it. but multiplying by 1 doesn't do anything, so we usually ignore it. Divided by the entire mass times 100% works out to be 25. Okay? So these should be pretty close to 100% when you add them up, right? Because the nothing in the compound should disappear. So you can always check yourself by making sure everything adds up to 100%. I have 2 more examples for you. Let's try this one, which is copper 2 bromide, CuBr2. So I'm going to erase our work here to make room. We'll have to get the mass of the compound again, so CuBr2. And I'm going to look that up here. CuBr2, molar mass, 223.354. Okay, let me write that down. 223.354 grams per mole. All right. This time we are worried about 2 elements. We are worried about copper and we are worried about bromine, and we need to find the percentage by mass of both. So copper's percentage is equal to the mass of copper, which is 63.5, I think it's 46. I can double check that in a minute, but I'm fairly certain that's correct. Multiplied by 1 because of our formula, and then divided by the mass of the entire compound, times 100 to get it into a percent. And before I calculate it, I'm just going to go check the periodic table to make sure that's the mass. Yep, 546. Excellent. Okay, 63.546 divided by 223.354. And just so you all know, I am doing this with a handheld calculator, so that's why you do not see the calculation going on, but it is happening. 28.45% is what I get out of that. And then we take bromine. And I do not know bromine's mass off the top of my head. 79.904. Okay. So 79.904 times 2, because remember, whatever's in the formula, divided by the mass of the entire compound, at 223, and then multiplied by 100 to get it into a percent, and this should end up with what, 71.55, but let's run the numbers to make sure. 79.904 times 2 divided by 223.354, 71.55. Yep. And I rounded a little bit. It's like 549, but it's very, very close. All right, last problem that we have is ammonium sulfide, NH4,2S. Okay, let's get that written out here. NH4 parentheses 2S. Alright, this one's a little different, right? Because we've got now 3 elements that we care about. The mass of this is 68.14, I think, to keep 2 decimals. I want to check 63 or 68. 68. Yep. Okay. Grams per mole. All right, we are worried about nitrogen. We are worried about hydrogen. And maybe I shouldn't say worried. We are curious, right? We don't worry. We are curious. No negatives. Okay. Nitrogen's percentage we'll start off with first. That is equal to the mass of nitrogen, 14.007, I think. I want to double check. Yep, 14.007 multiplied by 2, right? And that 2 is coming from 2 outside of the ammonium ion, saying that we have 2 of this whole thing divided by the mass of the entire compound times 100. And let's see what I get. 14.007 times 2 divided by 68.14. 41.11%. I'm going to circle this because there's going to be a lot of text on this page and I don't want it getting lost. So hopefully that makes it a little more apparent what that number is for you. The mass percent of hydrogen, yikes, Mr. Brester, stop drawing circles around each other. The mass of hydrogen is, the mass percent of hydrogen is equal to the mass of hydrogen times 8. And why 8? Well, we have 4 hydrogens in one ammonium ion, not molecule, one ammonium ion, and we have 2 ions per molecule. So total we have 8 hydrogen. And then it's divided by the entire mass and multiplied by 100. Don't forget the percent. So this is 1.008 times 8 divided by 68.14. I got 11.83%. I'm going to circle that one as well. Last one that we have, sulfur's mass percent is equal to the mass of sulfur, which is 32.06. I want to double check that one as well. There's a lot of these that I haven't used really since college, and I just am not quite sure. Times 1, right? 32.06, the mass times 1, we only have 1 sulfur, divided by the mass of our entire compound, times 100%, and the percentage that we get is 47.05%. That's what I got. 47.05. All right. So this math, right, isn't too difficult. I think it's just time consuming. And the one thing that I think you really need to watch out for is making sure that you read the formula. Oh, I think I just crashed my program. Okay, I'm not going to go try to get it back. You need to watch the formula to make sure, like for hydrogen, for example, we multiply by 8 because you have 4 hydrogen and then 2 of that ion. So you need to really be paying attention to the formulas that are written out and making sure that you multiply by the correct number. So again, I don't think that the math is terribly difficult, but the equation can be tricky because we don't often think of using those numbers like that. So I hope that this helps you, and be looking for next week when we do it in the reverse direction. As always, let me know if you have any questions